All right. Oh, here am I. Projectile motion, part 2, worksheet number 2. You're only going to do problem number 2. So I'm just going to do one problem. It'll be kind of a long one, but that'll be it. This will probably be a shorter video. And then there'll be some review worksheets later on that you also will do with this lesson. Anyway, I'm just going to do problem B on the notes for projectile motion. So we're still doing 3-6. And this is the fun problem. This is the one that you'll know what I mean in a minute. The one that, the practical, the cool experiment thing you can do. So you go outside and if you ever have those little like water rockets, you can still get those, you pump them up and put water in them and it shoots them off like that. Or they even have some with air. Well, if you know exactly what angle, all I have to know is what angle am I going to launch it at. And if I know the initial velocity, I can figure out many, many things about that. Or another way to think about it is a football, like coming to kick off a football, like someone comes there running and boom, they kick the football. The pathway that when you kick an object, like let's use the football for example. Kind of a weird looking football, kind of flat looking. Okay, that's a little bit better. All right. So I kick the football, and it's going to go up, and it's going to come back down. All right. So here are some points along the way that are important to know. First of all, we are going to have to know the angle of that. So yes, this is where sine, cosine will come back. All right? We need to know the angle. But if we know the angle, then we can actually figure out. We know the initial velocity. We'll have an initial x velocity and initial y velocity. When we know those two things, vx, vy. Vy. You kick it off at that angle, you know the velocity. You're going to be able to figure out how high it goes. That will be the height. What will be the highest point that it reaches. You'll also be able to figure out what's called the range. Remember I told you that in the last video. That's going to be the horizontal distance that it travels from there to there. And then you'll also be able to figure out how much time will it take. How much time will it be in the air, the hang time, from the moment it leaves the ground all the way to when it strikes the ground again, how much time will elapse? Those are all the things we're going to figure out from this. You can also figure out what will be the angle it lands at and all that kind of thing as well. But all right, so here we go. Let's read a problem, and we'll try it out. A rocket is launched at 21.5 meters per second at 32.4 degree angle, at a 32.4 degree angle above the ground. Okay, so I'm just going to draw I'll draw up here a little angle up. I don't want it to be too large because I'm going to need some chalk space to work out some stuff. Maybe I'll put it right here. I'll make a small diagram over here. So we're going to launch it this way, and we say that the angle, 32.4 degrees. Okay, the angle is 32.4 degrees. Now, that's your vector. We'll call it the velocity vector is 21.5 meter per second in that direction. Now you're going to have two dotted lines there. Well, I'm going to do it a little bit better. Vx and Vy. Now, it's going to go up. Then it's going to come back down again. All right, so it says, calculate the time, A, the time it takes for the rocket to reach the ground, and B, the distance from the starting point to the landing point. Okay, first thing you have to do is figure out what is the x and the y velocity. So that is something you saw back in the last chapter. If this is 21.5 meters per second, then, and that's 32.4 degrees, let's find out Vx and Vy, the horizontal and the vertical. So, you know that sine of 32.4, maybe I'll put it over there or something, well, whatever. Sine of 32.4 will equal Vy over 21.5. And cosine of 32.4 degrees will give you Vx over 21.5. So 32.4 sine is 0.535. And I'll multiply it by 21.5. So 0.535 times 21.5 equals Vy. And then here, cosine of 32.4 is 0.844 times 21.5 will give me Vx. All right, so my Vy, my vertical velocity, 0.535 times 21.5 is 11.5 meter per second. And my horizontal velocity, Vx, is 0.844 times 21.5, 18.1 meters per second. So 11.5 and 18.1. 11.5 is your vertical, and 18.1 is your Vx, or your vertical. All right, so we have the two things right there. Now, it's kind of like the free fall problems we talked about, and you'll see what I mean. Remember, there's two problems, like you want to do Vox-VAT or whatever, that there's a vertical, Vy, and then there's also a horizontal, Vx. They're two separate problems, but they both will have the same time, okay? So the first thing we can figure out is how long will it take to get to this highest point? And let's remember that. So let's just say that's the highest point. What will be the time to get to the highest point? And what you do, now I'll erase these so I have more space. I'm going to use the vertical, the Vy. Initial vertical velocity, as it's kicked, it goes up. At 11.5, it's going upward. Remember, this is like two velocities. One is up, going horizontal, and one is going up vertically. The vertical velocity is 11.5. Okay, so what I'm going to do is I know this. I know that if this is my vertical velocity, Vy, I'll put Vo. Vertical Y initial is 11.5. I know that to get to the halfway, the highest point, the halfway of the travel point, the velocity is going to be 0 at the highest point. And we know the acceleration is negative 9.81. So for the vertical, I might put the word vertical there. We know that you can go, you have initial velocity, you have final velocity, and you also have your acceleration. Acceleration vertical. Okay, so we can use this equation, V final minus V initial over time. And so I'll put it here. Okay, so negative 9.81. That's your acceleration, meter per second squared. For in the y direction, your acceleration is negative 9.81. Your final velocity is 0, and your initial was 11.5. And we don't know the time. We're trying to find that out. So the time, it'll just be negative 9.81 equals, or times t, equals negative 11.5. Now just divide them both by 9.81, negative. And the time is 11.5 divided by 9.81, 1.17 seconds. Now, this is telling me how much time to the highest point. Okay, so the time to the highest point is 1.17 seconds. All right. Total time of travel, I'll put hang time. Remember, hang time means in the air. Total hang time, or travel time, equals 1.17 times 2. You just double it. So 1.17 seconds to get up to the highest point, and 1.17 to get down. So 2.34 seconds. That's your total time that it's traveling. Now, so the first one, they ask you the time it takes to get to the ground. Okay, so that will be the time it takes from starting to get back to the ground. Again, it will take 2.34 seconds. Now, the time to the highest point will be 1.17 seconds, and you need to know that. In fact, I can call it time 1/2. equals 1.17 seconds. The highest point time is 1.17, and then you double it for the next part. Okay, so do they ask how high it's going to go? They didn't ask that, but we should have asked that for like ABC. So I'm going to go on and do it here. The height. The highest point. The highest. Maximum height. I'm sorry. Maximum height. The highest point, or the maximum height. Let's figure out what will that be. How high is it going to go above the ground when it's right here? Okay. Well, now we know everything. We know the time. So we can use any equation we want to. I would prefer to use this one. V final squared is V initial squared plus 2A delta X, but I'm going to make it delta Y because we're going vertical here. So you could have done this one without having the time, in fact, because I like to use that when it avoids putting the time and squaring it. So my final velocity will be 0. 0 squared equals the initial velocity, which was still 11.5. This is all vertical. So you might want to even label vertical when you're doing these parts and know which one is vertical and which one is horizontal. I'll show you the horizontal in a moment. Okay, 2 times negative 9.81, and we don't know y. We're trying to find the height is delta y. So we'll work these out. 11.5 squared is 132. 0 equals 132 plus, and we'll multiply 9.81 times 2. Negative, or minus actually, minus 19.6 delta y. Okay, this times this, 2 times negative 9.81 times delta y gives you negative 19. It's a negative, watch your sign. So then it becomes negative 132 equals negative 19.6 delta y. Then you divide them both by negative 19.6. And you get 6.73 equals delta y. 6.73 meters high. That's like more than, a meter is a little bit more than a yardstick would be. So that's like 3 feet, 18, 20 feet above the ground, somewhere around there. All right. So 6.73 meters. That's the height, the maximum height. Maximum height equals 6.73 meters. I know I'm going to probably ask you that on another question, even though I didn't put it in I should have put it in the sample. All right, and then the last question is, so we know how much time it takes to get to the entire travel, 2.34. Time to the highest point is 1.17. The maximum height, 6.73. Now we need to know the range. That is, how far away will the ball land? Okay, and to do that, that is a horizontal problem. I'm going to erase this. So the neat thing about this is the horizontal and the vertical do not affect each other, but they both happen in the same amount of time. So that's the part that you have to be, that's where they become the same. So here's an equation that's very good to use and to know and to realize. In the horizontal, as the ball travels, it said it started at 18.1 meter per second horizontally. Well, guess what? It is always going 18.1 the whole way. We ignore the air resistance. It's always going 18.1 until it hits the ground, and of course it stops. So it never accelerates in the horizontal direction. We assume that is true, and it shouldn't really at all. And it could slow down because of wind, and if it's a big, big wind, but we ignore that, okay? So, and it works out okay. If you did this with a calculation, we go outside and do a little rocket launcher and all that kind of thing. If a wind blows, well, then we say, I'll do it over again. But when you do it the other times, your prediction comes out right. So for the horizontal, here's the main equation. Is that velocity is displacement over time. It's actually the easiest one. Now, because in the horizontal, we assume no acceleration. So that means no acceleration. So that means that V initial, which was 18.1, is the same as V final. It's also 18.1. Therefore, it will also be your average velocity, which is 18.1. You don't have to write this part down. All of that's the same. 18.1, 18.1, 18.1. Because remember, this equation that said V initial plus V final over 2 is your average. Well, if it's 18.1 plus 18.1 divided by 2 is 18.1. So this is an important little statement to realize. But that's why we can just simply do this. The velocity in the, oh, I'll put an X there, in fact. Your average X velocity, I should put Vx. That's not, because this is not true for the Y. In the Y, you are slowing down. But for the X, Vx will be 18.1. The displacement is at delta x, the distance. Now the time, which time will I use? If I want to know the entire range, the distance, I got to use the total time of hang time, the total time, 2.34. Okay, so 2.34 seconds. So I'm just going to multiply those and I'll be done. 18.1 times 2.34 seconds is 42.3 meters is the range delta x. So, I know I went through a lot, and there's a lot of stuff. You might have to go back and watch the video again, but it's only 16 minutes, so you can go back through and watch it again. If you do number 2, that's all you got to do for the homework. Just one problem. It's just like this one. If you want to do number 2. It's number 3. I'm sorry about that. You already did number 2 yesterday. You do number 3, not number 2, number 3. And if you want to do number 4, you could. But let me just tell you, you don't have to do number 4. You don't have to. But on number 4, here's what happens is that it's a little bit different. Because on number 4, I'm just going to quickly tell you, and if you want to try to figure it out, you'll be real happy if you get it right. We're launching something from above the ground. Like we're standing on a ladder or something, you throw something. So then you got to remember this height right here. So when you will still go up to the same height up here, but then the time of travel to there, you're gonna have to you're gonna come all the way back down lower in that case. So you're gonna come lower than you started, and so that changes things. It's more of an advanced thing. You don't have to try that. Thanks a lot, though, you guys. Just do that problem number 3.